So yeah, like Tong mentioned, I'm a PhD candidate from UC Berkeley, and today I'll be sharing a bit about an R package I developed called eDNAjoint, which I'm hoping will be a useful new tool for modeling environmental DNA or eDNA data. This package is on CRAN, and we also have a manuscript about the package in Methods in Ecology and Evolution. So just to give a quick roadmap of today's presentation so you know what to expect. First, I'll go through my motivation for developing the package and why I think it will be useful. I'll share a few key features of the package. And you might have noticed that the word Bayesian is in the title. So the models that you can use in this package are formulated in a Bayesian framework. So a basic understanding of Bayesian stats is kind of necessary for using the package. So I'll give the world's quickest crash course on Bayesian stats and refer you to some additional resources. I'll go through one example workflow. This uses tidewater goby data from California. And this is just one of two example data sets that are embedded in the package. So you can kind of play around with them as well. And it's really useful for seeing how input data should be structured. I'll finish with some troubleshooting tips and final thoughts. And then if all goes to plan, we'll have some time at the end for Q&A. So I first want to start with a quick story about why the model underlying the package was developed, because I think some aspects of the story might resonate with folks who are collecting eDNA samples. And the story is related to the invasive European green crab, which is one of the world's most impactful invaders, yet early detection can be really challenging because it's a bit like searching for a needle in a haystack to find them. So a few years ago, eDNA was a really new tool, and we were curious about using it as a method for early detection of green crab. And green crab is a particular problem in the Pacific Northwest. So we collected eDNA samples at multiple locations throughout the state of Washington. And all of these sites are also locations of long-term monitoring programs where baited traps are used to catch and detect green crab. So there were a few sites where we detected green crab with eDNA, and green crab were also caught in traps around the same time that the eDNA samples were collected. There are also some sites where we detected green crab with eDNA, but not with traps. And then finally, there were some sites where green crab was not detected with either method. So some of these yellow sites were extremely surprising because they were hundreds of kilometers beyond where green crab had ever been visually observed. So we really didn't know what to make of these results. We were wondering if these surprising detections were real or if they were false positives. We also didn't know how to combine these two types of data in a meaningful way. So these types of questions are increasingly common. eDNA data has really exploded as a new source of information over the last decade. It's attractive as a potentially sensitive and efficient monitoring method. We've also seen this huge growth in private industry with dedicated eDNA services that have made kind of sampling gear and laboratory expertise much more accessible. But unfortunately, software tools designed specifically for interpreting eDNA data really have not kept pace with the broad availability of this new data source. So you've seen this huge growth in peer review literature of approaches that link eDNA data to quantitative estimates of species abundance and distribution. But these approaches are really kind of confined to academic communities with the technical expertise that is necessary to develop these bespoke models. And to date, the occupancy model has really dominated the analytical landscape for interpreting eDNA data for single species. This makes a lot of sense because the occupancy model is really useful for accounting for imperfect detection when assessing species presence. And then really importantly, there's just tons of really accessible software that can be used to and occupancy models. But occupancy models may not always be the most appropriate analytical method for interpreting eDNA detection data. So the rate of detection can often correspond to species density, not just occupancy, presence or absence. And thinking back to the green crab story, we often have observations from non-genetic data sets, which from here on I'll kind of refer to as traditional observations. And these kind of traditional observations often spatially and temporally overlap with some or all of the eDNA data. And existing software really has not yet facilitated the integration of eDNA data with measurements made by other methods. So eDNA is really this kind of new type of information that presents new opportunities and new challenges with interpretation. So to address this problem, my co-authors and I developed a model that integrates multiple types of data in a way that they can mutually inform each other. So the idea is that both eDNA and traditional data are generated from the same ecosystem state. And both of these survey methods give us imperfect measurements. So this model provides kind of a formal way to integrate these two data streams and quantify uncertainty in both detection methods. And one benefit of jointly modeling these two data types, so we can make these really direct comparisons and better understand the relative sensitivities of the two survey methods. So just thinking about kind of more of the features of the package. So these two data streams are used to jointly estimate parameters in the model. And one of these parameters is the expected catch rate at a site, which we call mu. So this catch rate is kind of analogous to species density, but this is kind of this unobserved latent state since both survey methods imperfectly measure species density. Another important parameter in the model is the probability of false positive eDNA detection, which we call P10. So the model is intended for use with replicated, paired eDNA and traditional observations at multiple sites across the landscape. So here are these primary sample unit. These are your sites. Ideally, you'll have sites with a range of species densities, including those where the species is absent or at very low density. So you can kind of get a sense of the lower limit of detection with both methods. And then within each primary sample unit, you also have secondary samples. So for eDNA, this will be multiple water samples. For traditional samples, this would be multiple survey replicates per site. So this can be multiple traps, multiple electrofishing surveys, multiple point counts at each site. And then finally, for each eDNA secondary sample, so each water sample, you'll have replicated observations. And these, right now in the package, they're just binary. So this is detection, non-detection. These are kind of our PCR replicates in each water sample. So these are kind of the basic data requirements, but there are multiple variations on this model. One of these allows for site-level covariates that scale the sensitivity of eDNA relative to traditional sampling. So maybe you've collected data on flow rates, average temperature, or turbidity at a site. And you want to see if these variables increase or decrease rates of eDNA detection relative to sensitive traditional surveys. Or perhaps you have multiple gear types and you want to account for the different catchability rates of these methods. And then finally, the model allows for semi-paired data. What I mean by this, these are scenarios where you have traditional samples from some sites, but not all. So this means that you can make predictions about species density at sites where you've only collected eDNA data. So really kind of the primary function of the package is this function called joint model. So it's going to be used to fit these models to your data. We also have a few additional functions that can be used to interpret model output. And for the demo today, I'll be using data from a 2016 study on these super adorable, tiny, endangered tidewater goby fish in California, where both sane net samples and eDNA samples were collected at multiple sites around the state. And authors also collected a bunch of information on site-level covariates, so things like salinity and water time that might affect the rate of eDNA detection. So as promised, I just share a few key concepts about Bayesian statistics. At the bottom of the slide is a link to the section of the user guide that contains more information and resources. Also, in general, that user guide has tons of information about the package, the background, the model underlying the package, and different examples of how to use it. But anyway, so just kind of quick crash course. The Bayesian paradigm differs from the frequentist paradigm in a few key ways. And for context, if you're used to maximum likelihood approaches, that falls under the frequentist paradigm. So if you're a Bayesian, all parameters are treated as random variables. This means they'll be encoded as a probability distribution. This is different than the frequentist paradigm that assumes parameters are fixed and uncertainties kind of entirely attributed to our estimation of those parameters. And then similar to that point, in the Bayesian paradigm, we characterize the distribution of model parameters given the observed data. This is different than frequentist statistics, where we characterize the value of parameters most consistent with the observed data. And then really importantly, the Bayesian framework encodes this idea of a prior belief that can be updated based on data. So I kind of drive this home a little bit more. Here's Bayes' theorem put a few different ways. So the posterior, this is what we're trying to estimate. So these are the probability distributions that best describe the model parameters given the data. And the prior distribution goes into this calculation. So this is the way that we kind of encode our prior beliefs about model parameters. And this is kind of really important to consider because it really can affect our inference. And with the models in this package, you can specify prior distribution for some of these parameters. So it's really important to be kind of deliberate about how you're doing that. Okay, crash course almost done. I just want to give a kind of a quick glossary of some of the key terms I'll be using today. So MCMC, Markov chain Monte Carlo, is the algorithm that we use to approximate or kind of estimate the posterior distribution. The MCMC algorithm generates samples of the posterior, which is kind of just a long string of numbers that we can use to summarize or characterize the posterior. We often run multiple chains of the MCMC algorithm since this algorithm is stochastic. So we can use these chains to assess if the algorithm converged. And then finally, all the models in the package are specified with this probabilistic programming language called STAN. So once you've fitted the model to your data, the kind of resulting object is a STAN fit object. And this is really nice because it kind of opens you up to kind of the RSTAN world and allows you to kind of use all of the functions within the RSTAN package with your model fit object. Okay, so now onto the fun stuff. We're going to do a quick demo. This link is off here, but I will move into R now. So I'm going to be going through the R Markdown version of the demo. There's also the rendered PDF that's in the repository as well. So if looking at live code being run is chaotic to you, maybe it's helpful to follow along with the PDF simultaneously. Okay, hopefully this is big enough for everybody to see. So first step, we're going to load the R package as well as some other packages that we'll be using today. And the first thing to think about is kind of preparing the data. So making sure that your data is properly formatted is really important for making sure that the package works as you expect. So again, there's a few data sets that are embedded in the package. One of these is the tidewater goby data. So we can see we're loading the data, looking at the structure. We see that it's kind of a list of matrices. We have our PCR, eDNA data. This is the count, traditional observations, and we have our site level covariates. So again, this is kind of the list of 4 named matrices in your input data. So let's first look at the count data. So this is the kind of net samples, and we have the number of rows is the number of sites. So here we have data collected for 39 sites, and kind of the number of columns, that's the number of secondary samples. That's the number of kind of replicated net samples per site. And the maximum number in this data set is 22. So again, each of these numbers is the number of gobies or the count of gobies in each, say, net sample at each site. So here again, we have the number of rows, or the rows are the sites, the columns are each replicate per site. So the way that they collected this data, they didn't collect the same number of kind of replicated observations each site. So we're kind of using these NAs to indicate which sites had fewer than the maximum number of replicate observations. So, for example, at site 1, we only have kind of 11 replicates, and we filled in the rest with NA. Site 11 had the maximum number of replica observations, which is 22. So we look at just row 11, we see that we have no NAs in that row. So moving on to the eDNA data, this is divided into 2 different matrices in your input data. PCRN is the number of PCR replicates per water sample per site. So these are kind of the PCR attempts. So if we look at this matrix, let's look at the bottom of this matrix this time, we see sites 34 to 39. Again, the maximum number of water samples they had was 22. We're kind of indicating the fact that the number of water samples collected per site is uneven across the landscape. So we're filling in these empty spaces with NAs. And 6 is the number of replicates for most of these samples. So again, let's say we're looking at site 4, water sample 6. There were 6 PCR replicates in that water sample. So those were kind of the number of attempts. We also have the number of PCR successes. So this package works with just detection, non-detection data, so just zeros or ones. So the question is, of the number of PCR replicates, how many detections were there? So looking at the bottom of this matrix, we see, again, filling in the missing data with NAs. And this is the number of the number of replicates, how many of them were successes, how many detections did we have? So for example, it's site 4, oops. So yeah, site 4, column 6, there of the 6 kind of PCR attempts in that water sample, 5 of them were positive detections, and we had 1 kind of no detection. So just kind of, there's a few checks you can do to make sure that your data is structured correctly before you use it. So kind of the locations in the matrices of the NAs, for the locations of the NAs in these matrices should match each other for the eDNA data. So this is saying that, you know, if you have attempts in kind of site 4, water sample 10, that matches the fact that you have detections or non-detections in the same location in your kind of success matrix. And then all of your matrices show the same number of rows. This is the same number of sites for all of your matrices. I mentioned previously that we can account for kind of semi-paired data. So that means you have some locations where you have eDNA samples, but no traditional samples. So the way that you would indicate that in your data is just to have kind of rows of all NAs. Okay, so we finished with the input data for the count data and the PCR data. This data set also has site-level covariate data, which is optional, but it's kind of useful for demonstration purposes here. So looking at the top of this matrix, the authors collected data on salinity, filter time, so it's kind of the time it took for the water to filter through the filters, the density of other fish, the habitat size, and kind of this vegetation covariate, which is the presence or absence of vegetation. This might look funny to you. You can't have negative time. So what I've done is normalized all of these covariates. So for each column, that means a mean of 0 and a standard deviation of 1. So this is kind of to help with kind of interpreting the parameters in the model and also just with the stability of the algorithm. So highly recommend normalizing these continuous variables. Okay, so just kind of looked at the structure of the data. There's more examples and kind of more detail about this in the user guide, but also happy to answer questions. So the next step is to actually fit the model to our data. So this function joint model, this is really the primary function of this package, and it kind of takes a few key arguments. So the first is our data. So this is our list of matrices that we just went through. You can specify which kind of covariates you want to include. So you could input all of your covariates, but include just a few of them in each of the model fit. You can specify the family. So this is the probability distribution used to model the traditional data. So here, this is the same count data. So options include a Poisson, negative binomial, and a gamma distribution if you have continuous, if your traditional observations are continuous. Another argument is the kind of the way that you can specify the prior distribution for the probability of a false positive. So the P10, it's modeled with a beta distribution, and the default parameters are 1 and 20. This is a kind of a relatively uninformative prior distribution. We'll talk more on this later. So for now, maybe just punt that to later in this demo, and we're going to stick with the defaults here. You can also, if you have multiple kind of traditional gear types, let's say you have net type 1 and net type 2, here you can indicate whether you have multiple gear types. So I'm going to start running this model. So again, running joint model, we have our goby data. Here I'm going to run this with just filter time and salinity. I'm going to choose a Poisson distribution to model the traditional data. We're sticking with the default priors or the default prior for the probability of false positive. And we ran that on multiple cores. So we ran each chain on a different core on the computer. And creates this really long output, but it's kind of nice. You can see the algorithm running, going through the warm-up samples and the actual sampling samples, and we can see all of our 4 chains running in parallel. So there are many more arguments to this function. Most of them are related to customizing the MCMC algorithm. but kind of the ones that I went through are really the primary arguments that you'll want to be thinking about. So the return object for that function is this object goby fit cove1. So let's take a look at it. So this contains two things. One of them is our model fit, and one of them is the initial values that were used to start the MCMC algorithm. So just looking at the first element of this list, this is our model fit, and it's of class stand fit. So again, this is really useful because we can now interpret this model fit with all of the functions in the rstand package. And the second element of this list are the initial values that were used to start the MCMC. So this is of length 4 because we have 4 different chains. Ideally, you'll have each chain start in a different place. And there's more information about the initial values in the user guide if you want to be setting your own. Okay, so we've ran our model. Now we have our result. In this first model, we use salinity and filter time as our site level covariates, but perhaps we want to compare this to a model that includes other covariates. So I'll get this second model started, but in the second version, where instead of filter time and salinity, we're going to be using this vegetation covariate. So this is kind of the presence or absence of vegetation. This verbose argument also might be useful, so it doesn't print out a bunch of messages. As you can see, it's shorter this time. Okay, so we've fit 2 different models. Now we want to compare them. So we can use this joint select function to compare our 2 models, see which one is a better fit. So this function takes one argument, which is a list of our 2 models. So model 1, model 2. This started. So what's happening under the hood here, it's model selection with leave one out cross-validation. So this is kind of a measure of how well your model predicts new unseen data. So a higher ELPD, this is expected log predictive density value, indicates better performance. This means that the model is better at predicting new data. It's kind of a better fit to your data. So this column is kind of the difference between the two. Since the ELPD is higher for model 1, we have 0 here. So this indicates to us that model 1 is, the structure of model 1 is better at predicting our data. So you can imagine testing this out with all of the covariates or none of the covariates to see which covariates you should be including. But for now, we'll just stick with model 1 where we have salinity and filter time. So the next step is to kind of look at our estimates. Here we're going to look at the posterior summaries of the different parameters in this model. So this model fit object contains our posterior samples. So again, this is just kind of a long string of numbers that are the kind of approximation of the posterior distribution. So we can use this joint summarize function in the package to create summaries of these marginal posterior distributions. So we'll first look at the P10 parameter. So this is the probability of a false positive. So this takes our model fit and this specification of the parameter. And we see that the kind of mean of the posterior is 0.003. So there's kind of, the mean probability of false positive is 0.003. We have our standard deviation of this posterior, the lower and upper bounds of the 95% credibility interval. We have the effective sample size. So this is essentially the kind of efficiency of the MCMC algorithm. Higher is better. And then R hat, this is really kind of the important, it's a really important diagnostic for understanding if we can really trust these results. So it's telling us if the algorithm converged. Ideally, we want an R hat less than 1.1. So it looks like we're good here. So we can plot these posterior samples. This is our marginal posterior for P10 as a density plot. So again, with Bayesian statistics, parameters are not just values; they are encoded as probability distributions. So x-axis is the value of P10. And next, we're going to look at a trace plot of P10. So this is really useful for, again, just kind of diagnosing the algorithm, making sure that we can trust the results. This plot is called a trace plot because it shows kind of how it's a trace of how the algorithm is moving through parameter space. So on the x-axis, we have our MCMC iterations. So again, it's just a long string of numbers. On the y-axis, we have the kind of value of P10. So this is really kind of tracing the algorithm moving through parameter space. And the way that this looks is kind of exactly what we're looking for. So each color is a different MCMC chain. We want this to look like a fuzzy caterpillar, which what this looks like to me. So we're looking for this trace plot to be stationary. That means that these chains are kind of moving around the same mean with the same variance. So these trace plots are super useful for both kind of sanity checking of that we can rely on these results, that the algorithm has converged, and also if it hasn't converged, trying to diagnose what's happening. So highly recommend creating and using trace plots. Okay, so we just looked at the parameter for P10, and now we're going to look at the posterior summaries for mu. So this is the expected catch rate at a site. So this is kind of our species density at each site. That is this kind of unobserved latent state that both the eDNA and traditional observations are mutually informing. So we have an estimate of mu for each of our 39 sites, 1 through 39. We can again see the mean of the posterior, the lower and upper credibility intervals, effective sample size, and R hat. And if we kind of scroll down, we see that it appears we can trust our results. The algorithm converged. Our kind of important R hat diagnostic is less than 1.1. So next, we want to interpret the site level covariates. So beta is the parameter in the model that scales the sensitivity of eDNA samples relative to traditional samples, and it's kind of it's a function of our covariates. So the way that our covariate data enters the model, it's kind of this linear regression where we have beta for site I is a function of the filter time at site I and salinity at site I. We have this regression intercept and the coefficients for these two covariates. So the way that this linear regression is in the model, it's beta is in the denominator. So as beta increases, the sensitivity of eDNA sampling decreases. So a positive regression coefficient would indicate an inverse relationship between the value of the covariate and the relative sensitivity of eDNA. So we can look at we can summarize the posterior for the different alpha coefficients and intercept. So again, we have the mean, credibility interval, effective sample size, R hat. And alpha 1 is the regression intercept. And this indicates the sensitivity of eDNA at kind of the average site. Alpha 2 is the regression coefficient for the filter time. So we see that this is positive, both the mean and the entire 95% credibility interval is positive. So this means that at sites where filter time is longer, the sensitivity of eDNA relative to traditional sampling is lower. This makes a lot of sense. If you have more turbid water, that it takes longer for the water to pass through the filter. This often means that we have some PCR inhibitors. So this kind of makes more sense. So longer filter time, less sensitive eDNA. Alpha 3 is the regression coefficient for salinity. So we see that this is negative. The entire 95% credibility interval is also negative. So this means that at sites with higher salinity, the sensitivity of eDNA is higher. Again, this also makes sense. This is intuitive. Salt is a DNA preservative. So if at a more saline site, eDNA lasts longer in the water, persists longer, so that likely leads to higher detection rates. So really what's useful here is kind of interpreting the direction of these regression coefficients, but this is still kind of a little bit abstract. So there's a few functions in the package that kind of make these comparisons of relative sensitivities a little bit more concrete. So one of these is a function called detection plot. So this is useful for finding kind of the units of survey effort. So by units, I mean number of water samples, number of traditional samples that is necessary to detect presence of the species with some probability. And here when I say detecting presence, I'm referring to kind of producing at least one true positive eDNA detection or catching at least one individual in a traditional survey. So we can make this calculation for an average site. So again, if we think about the way that these covariates enter the model, and again, we normalized our covariate data. So a mean site would have a filter time of 0 and a salinity of 0. So kind of if we're thinking about this calculation for an average site, this means 0 filter time, 0 salinity. So this function here is calculating the number of water samples and number of sane net samples needed to detect goby presence with 0.9 probability. And it's important here that this calculation is kind of given mu. So this is not an occupancy model. The rate of detection is a function of species density. So we're kind of saying, given a certain species density, how many survey units should we collect to detect presence? So we're going to run this. So again, the arguments are our model fit. This will become maybe a little more obvious when you see the result, but we're going to calculate this for a range of species densities. We're going to make this calculation at an average site. So this is kind of the filter time is 0 and salinity is 0. And we're going to ask how many survey units should we collect to detect presence with 0.9 probability. Okay, so these are the results. On the x-axis, we have the species density. This is the expected catch rate. Y-axis, we have the number of survey units necessary to detect presence. And the two different colors correspond to the survey type. So coral is eDNA, and the blue, I guess, the traditional samples. So just to help with this interpretation, so for example, let's say the species density, the expected catch rate is 0.25 gobies per net. It would take around, this is 6 water samples and 10 traditional samples to detect species presence. Let's say we have a different site where the species density is higher. So now it's 0.5 gobies per, the expected catch rate is 0.5 gobies per net. It now takes 4 water samples and 5 traditional samples to expect to detect presence with 0.9 probability. So kind of the takeaway of this is that, eDNA on a per sample basis is more sensitive than a traditional sample if you want to collect, if you want to be detecting the goby presence. So we just made those calculations for an average site, but what about if we want to consider a site where it's more turbid? So if we want to detect presence at a site with a higher filter time, because of our covariate data was normalized, we're going to make this calculation for a site that is 0.5 z-scores above the mean. So again, kind of the way this is entering the model is if the salinity is 0 and the filter time is 0.5. So this is a site with a higher filter time, a more turbid site. So we're going to run this function again, same kind of range of species densities of mu, and higher filter time. So 0.5 this time instead of 0. So these are the results again, x-axis, species density, expected catch rate, y-axis, number of survey units necessary to detect presence, and color are the two different survey types. So previously, we saw that eDNA was more sensitive than traditional samples. The entire coral line was lower than the blue line, and now they're about even. So again, this is if the expected catch rate is 0.25 gobies per sample. It now takes both 10 water samples and 10 traditional samples to expect to detect presence. So again, this makes sense. More turbid sites, eDNA becomes less sensitive relative to traditional samples. We can do the same exercise for salinity. So this time we're going to be considering a site that is more saline. So we're going to indicate this by updating this co-val argument to be 0 and 0.5. If we were to compare this to our first plot that was calculated for an average site, we would see that this coral line is a little bit lower. So now we need fewer water eDNA samples to detect presence relative to traditional samples. So again, this just kind of helps us make a little bit more concrete the model results. So this is kind of taking your posterior and doing kind of these post hoc calculations to help you interpret the relative sensitivities of the two survey methods. Okay, so previously we stuck with kind of the default prior distributions for the probability of false positive, and I promised I would talk a little bit more about this and not just punt this. So this is kind of the same code as above. Here's where we specified the prior distribution for the false positive, and this is the default for this argument. And these two numbers are the shape parameters of the beta distribution that reflects our prior belief about the probability of false positive. And again, this prior belief is updated with our data to give us our posterior estimate. So just to make a plot of what these shape parameters are referring to, this is a probability density function of this P10 prior given shape parameter, our shape 1 and shape 2 parameters being 1 and 20. So this is really saying that most of the probability density is less than 0.2. So this is really just kind of, us as researchers were expressing our belief that the probability of false positive is likely less than 0.2. So just to kind of make this calculation more precisely, 99% of the probability density is less than 0.2. So I would consider that prior to be relatively uninformative, but you could also use some data to create the prior. So perhaps from negative controls. Let's say you did some PCR negative controls or collected water sample, like blank water samples and ran PCR. You could use those negative controls to inform or to kind of create a prior for the probability of false positive. So for example, let's say you have 25 negative qPCR controls when you were processing your samples. So here we can kind of include this data in the model by saying that the probability of false positive is likely less than 0.04 or 1 over 25. So here we could kind of create a prior where the probability that P10 is greater than 0.04 is very low. So this time, let's use kind of shape parameters 1 and 100. And so you can see the probability density of this. So here, most of our probability density is less than 0.04. So this is kind of a scenario where we can use data about your negative controls to kind of encode a prior belief about what the probability of a false positive is. So if you have an informative prior, it's pretty good practice to do a prior sensitivity analysis. So here we're testing how sensitive our posterior inference is to the choice of a prior. So if the posterior is not sensitive to the prior, this means that the posterior is driven more by the data or more by information in the data rather than by the choice of prior. So we could run our model again. I'll just get this going while I talk. So we could run our model again with different priors. So here we're specifying a new prior. This one has a larger variance than the default specification. And we can do this third option. Oops. This third option, this one has a smaller variance than the default. Let's give this a second to run. Okay. So we're next going to kind of compare the posterior estimates of P10. So again, we are running the same model with the same data, but with different prior distributions, and want to see if this prior distribution choice affects the posterior estimate. So this fit one, this is our original version. We have the mean of 0.003, 95% credibility interval from 0.001 to 0.007. Version 2, kind of see that it's pretty similar. And version 3, again, qualitatively pretty similar. I think a better way to really view this is to plot the prior and the posterior side by side. Which this was not quite so big, but anyway. So on the left here, we have our 3 prior distributions. So these were the 3 three models we just ran. These are the probability density functions for each our prior specifications. We can see that they're quite different, have different variances mostly. And these are the posterior estimates for each of those three models, kind of with the same x-axis. And we can kind of see that they're really kind of strongly overlapping. So I would interpret this as our inference being more driven by the data rather than choice of prior. So this means our posterior is pretty insensitive to the choice of prior. I think it's really kind of useful as just, again, sanity check to make sure that your prior is as informative as you want it to be. And of course, if a prior can be informative if you have data to support the development of that prior. Again, there's more kind of information about creating these plots, doing a prior sensitivity analysis, understanding those shape parameters in the user guide. But I just wanted to highlight that prior sensitivity analysis is probably useful. Okay. I will now return to slide mode. There we go. Okay, so just a few troubleshooting tips. Bayesian statistics can be kind of finicky. The algorithm does not always converge. So there's some different indications if your algorithm hasn't converged. You can, with a kind of really important diagnostic, that R-hat value is really informative for understanding if you can rely on the results, looking at trace plots, et cetera. But some tips are trying out different families to describe the data generating process for the traditional survey data. So in this first version, we used a Poisson, but maybe your environment is really patchy and you have some replicate observations are really, really high and some are really, really low. So you'd expect kind of a large variance in your traditional observations. You could test out a negative binomial. So there's kind of different things you could play with a little bit to if things aren't working. You could change the prior distribution for p10s. This is the probability of false positive, particularly if you have data to inform the prior. You can set better initial values from the MCMC. So if you start the algorithm in a place that's really, really far from where it should end up, things can go a little bit wonky. So there's some examples of how to think about starting the initial values for the algorithm if it appears that the model is not converging. You could increase the number of warm-up samples. So you start the MCMC algorithm, it starts kind of moving through parameter space. Particularly if the place where you start is really far from the global minimum, you might want to discard those initial samples. Final tip: you can create trace plots. We love trace plots. The package ShinyStan is really, really useful. So again, these models are written in Stan. The model object is a StanFit object. So this ShinyStan is basically a Shiny app that helps you explore the trace plots, the posterior kind of density plots, has a bunch of different diagnostic and troubleshooting tools. So I highly recommend looking at ShinyStan if you're trying to diagnose problems. And you can also email me. Here's my email. But I think that's about everything. These workshop materials are in this GitHub repository. Definitely refer you to the user guide. This is where lots of information is. And you can also email me. It's really, really useful to get feedback from people that are using it, both kind of to update the package itself, but also write better documentation and examples. And also, if things work for you, you can also email me, and it'd be nice to share success stories. But I guess it's now a good time to answer questions.
Okay, there's two questions on the poll everywhere, I see. First question is, what causes false positive in this kind of data, not just human error, and why did you name the parameters P10, and why a beta? Wow, that's very specific. Why do you use a prior for beta 120?
All good questions. False positives. I mean, this is kind of just the number one concern for eDNA. It's why a lot of people don't really trust it. They're very skeptical. So I think kind of by having this, by actually explicitly estimating it as a parameter is really useful. So false positives can kind of come from, you can kind of consider two different types of false positives. One is more from kind of like the laboratory end. So that's just kind of the human error. Let's say you, like in this goby example, let's say you have just like goby data or DNA just like all over the lab, and you put your glove on the surface of the lab and you touch your pipette, and then just, that can kind of contaminate your samples. So that's kind of like the laboratory false positive. And ideally, you'll have protocols for kind of limiting that. So it's kind of human error. So it's kind of one type of false positive. The other is more kind of like an environmental false positive. That's a little bit harder to, a little bit, it's not really human error. So let's say, for example, you're collecting water samples in a river, and you're, let's say there's like gobies upstream, and their DNA is being is traveling down the river to where you collected your samples. And even though where you collected your samples, there's no gobies, but they're upstream. So that's kind of that is also kind of considered a false positive, where it's kind of eDNA that's traveled from one location to another and is being introduced into your sampled area. Why named the parameter P10? So it's kind of conventional for these types of hierarchical models. So P, probability, 1 meaning that you detected the species, and 0 meaning that it's not actually there. So I think kind of in the lexicon of, I think also like occupancy models, that's kind of a way to specify that like maybe a 0, 1 would be a false negative. That that's kind of the contrast. And yeah, the beta 120 prior, a mildly arbitrary choice as something that is kind of uninformative. If you were to have a completely uniform prior, the algorithm probably wouldn't converge unless you had really, 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 really good data. So I think this is just a way to say we expect the probability of false positive to be pretty low, likely less than 0.2. In my mind, that's not an informative prior. But I also think that highlights the value of doing a prior sensitivity analysis to make sure that it's this kind of somewhat arbitrary choice of a prior is not, significantly impacting your estimates.
Thank you so much. Okay, let's see. There's one additional question. Could you go into the mechanisms behind why the turbate state prohibits eDNA detection? The audience would have thought that perhaps the DNA would stick to the particles and so would be more likely to be detected. But it sounds like that's not the case.
Yeah, I feel like for so many environmental variables, there's examples of like why it would increase detection or decrease detection. I think a lot of arguments could be made either way. I guess both from my experience and what I've read is that so tannins are common in water, and that's kind of in a lot of really like highly sedimented locations. And tannins are PCR inhibitors. So if you have tannins in your sample, then it can inhibit the PCR reaction. So I guess, more turbidity, is more likely to have PCR inhibitors in the water, kind of due to the extra stuff. But yeah, I think like the hypothesis that DNA would stick to particles is also a good one. I think it's just true of a lot of covariates. There's logical justifications for either way.
Okay, thank you, Abby. And the next question is, can this be used on meta-barcoding dataset or only for qPCR?
It can be sort of meta barcoding data sets. I think it really it only handles presence, absence, eDNA detection data. So it's not if you have like continuous eDNA concentration, it wouldn't work for that. If you have meta barcoding, you would probably need to run the model once for each species. rather than running multiple species all at once. But yeah, it would work for metabarcoding data if it's binary detection, non-detection, eDNA data, and you would just have to run separately for different species.
That makes sense. Thank you. And also, another related question. You can also use a package to compare multiple non-eDNA sampling methods from the audience. Can this method be used for other non-eDNA sampling methods? Because you talk about how that can be used for other approach like metabarcoding.
Um, yeah, that's a good question. I think so. Really, it's the model is combining count data, replicated count data, and replicated presence absence data. So I guess I would say yes, but you'd still have the probability of a false positive. Or so I guess if whatever method you have yields detection, non-detection, binary data, and you're also concerned about false positives, then yeah, it would work. I'm kind of curious about like use cases for that, but yeah. So again, it's really just combining count data and binary data, and considering that the binary data could produce false positives.
Yes, thank you. Yeah, I guess the audience is just wondering if there's any other applications beyond just specifically use that for eDNA sampling. That's why the question is asked. Okay, thank you. And also the next question, in the demo, you discuss average probability of detection across sites, but could you include a site as a covariate itself to see how much site influence detection? So, or would you recommend using features of the site like temperature?
That's a good question. I think if I understand correctly, that's kind of more site as a random effect. Um, so right now you can't include site as a random effect, but I think maybe if there were um, reasons to group sites that weren't necessarily like related to a feature of the site, but maybe there's some sort of qualitative description, you could probably include that as like a covariate or a fixed effect. But yeah, so the way that I'm reading this, um, you can't just it's if you're thinking about site as a random effect, you can't include it in that sense, but only as kind of shared. Yeah, it could be like a categorical feature of the site. If that makes sense.
Yeah, that makes sense. Thank you so much. Let's see. There's one more question that just submitted. So is can the model run without replicates of traditional survey data? So if so, how important are replicates of the traditional survey data? Think about the use for research cruise data and also where costs are high and also operations take long for a single sample.
Yeah, you definitely can. I probably should have shared that, and I've seen an example of where that's the case. I think probably what would end up happening is that you would just have more variance in your estimates. So it's just kind of one, like it's just one replicate. But yeah, you could definitely.
Okay, I think we are all caught up on the questions.